in UTC time. So let's start.
Recording in progress.
Okay, got it. We're going to start this section now. It's the second day of Seminar 6, and I appreciate you all guys returning from yesterday. So that's very good. And the first talk will be given by Doron Quain. He is a physicist from Israel, from the Ben Gurion University. And we all met him personally already in the laser physics meeting, so we know him. And today he's going to tell us about quantum irreversibility of quasi-static protocols. So, Quain, you have the 30 minutes, and I will give a warning when it's 5 minutes to that time. Okay? You can go.
Okay, the camera is okay?
Everything is fine.
Good. So I thank the organizers for the opportunity to present this recent work about quantum irreversibility. It has been done by my PhD student, Joshua Winston. You have here the references, and the PDF of the talk is also available in my homepage. Let's start with a textbook paradigm of irreversibility. Say you have particles inside a cylinder, and there is a piston, and the control parameter is the position of the piston. So we move the piston out and then back again, and we ask whether the process is reversible, whether we come back to the initial preparation. And the standard answer is that the quasi-static limit is adiabatic, and therefore in this limit we have reversibility. But this assumes that the system is globally chaotic and ergodic, and in general this is not the case. In general, phase space has mixed regions of chaos and quasi-regular motion. So in the quasi-static limit, actually, the reversibility is horrible. It is very not reversible. It is very irreversible. I will demonstrate it in a moment for the system of interest. But what is the question that we ask? We ask what happens quantum mechanically. Now, you might think that quantum mechanically you have quantized energy, and therefore there is a adiabatic theorem that tells you that in the quasi-static limit you will have adiabaticity and reversibility. But we are interested in a mesoscopic system, many-body system with very, very, very dense spectrum of energies. And therefore, it is not possible really to satisfy the quantum adiabatic condition. So we ask what happens, and one possible answer is maybe it will be like the classical. Maybe we have a quantum classical correspondence. And as you understand, my statement is going to be very different. I claim that there is a major breakdown of quantum classical correspondence, and there is a novel regime of quantum irreversibility that is very different from the classical. So what is the system of interest? We are dealing with a lattice ring, and we condense, the experimentalist can condense bosons into the zero momentum orbital of the ring. So initially there is no current in the ring. Now the experimentalist can also rotate the ring. So the rotation velocity is our control parameter. we increase gradually the rotation velocity of the ring beyond the critical value where we start to get current. And then we decrease back the rotation to zero, and we ask whether we come back to the initial zero momentum condensation. Now, if we were dealing with superfluid helium, then you know what is the critical velocity that you have to rotate the ring to get current. This is the theory of Landau. There is Landau criterion. This ring is more complicated because it is a quantum chaos system. I will explain in a moment. So the theory is more complicated. It had been worked out by my former student, Geva Arwas. But what we're talking today, the work of Yehoshua, is what happens if we gradually increase the rotation of the ring beyond the critical value and then decrease it back to zero. That's the question. So that's the Hamiltonian of the system. We assume that it is described by the Bose-Hubbard Hamiltonian. We have on-site interaction, and we have hopping between the sites. Below, you see various configurations that we have considered in past studies, but today we deal with a triangular ring. So if you regard these bosonic sites as classical oscillators, you can write classical equations of motion for the oscillators, you can rescale parameters, and then you see that there is only one dimensionless parameter that controls everything, which is the ratio between the interaction and the hopping. But if you do second quantization, meaning that, well, it is a quantum problem, quantum bosonic sites, then there is a second parameter that plays the role of H bar, and it depends on the number of particles, and we assume that the number of particles is very, very, very large. So we are deep in a regime where you expect quantum classical correspondence far away from any quantum phase transition. But I'm going to claim that nevertheless, there will be a major breakdown of quantum classical correspondence. And there are not many examples for major breakdown of quantum classical correspondence. The other example that I can have in mind is dynamical localization. But this is not the issue here. Here, the major breakdown of quantum classical correspondence has to do with a mixed phase space of chaos and regular motion. So here I write again the Hamiltonian for the three-site ring. Our control parameter is the rotation velocity of the ring. It is a rotating ring. So if we go to the rotating frame, we have there a Coriolis force, which is like magnetic field. And this has some flux. It is called Staniak phase. It is analogous, if you wish, to the Aharonov-Bohm flux. And this flux, or Staniak phase, enters into the hopping between the sites. So you can write the Hamiltonian also in momentum representation, and then you see that the rotation velocity enters into the energies of the orbitals of the ring. So this ring has three momentum orbital. Initially, the ring is not rotating, and all the particles are condensed in the zero momentum orbital. Now we increase the rotation frequency, and the zero orbital becomes metastable. And then, in a later stage, as I will describe in a moment, you will have a depletion. And this depletion is actually what determines the critical rotation velocity that I mentioned in the previous slide. So there will be depletion, and then we decrease back the rotation frequency, and we ask whether we come back to the initial state of condensation. Now I will use, in order to describe the simulations, I will use two coordinates. One coordinate is the depletion coordinate, which is the total occupation of orbital number 1 and orbital number 2. And M is the population imbalance. Now I would like to make a remark about the Hamiltonian. If you do the Bogolyubov approximation, which means to keep in the Hamiltonian only the part of the interaction which is called pairing, meaning that the excitation is by taking pairs of particles and excite them to the upper orbitals. Well, the pairing interaction of Bogolyubov, the population imbalance, is constant of motion. So Bogolyubov provides integrable approximation for the Hamiltonian. But of course, there are additional terms that generate chaos. And as I will show you, these terms that are neglected in the Bogolyubov approximation are very important for the understanding of what is going on. So let's describe what happens in this protocol of increasing and then decreasing the rotation velocity. So just for pedagogical purpose, let's assume really that we have just 4 particles. If we have just 4 particles, then what you have here on the right are the many body energy levels of the system for various values of the rotation velocity. So initially you have 0 rotation, and the lower level is having all the particle condensed in the 0 momentum orbital. So now you increase the rotation, velocity of the ring, and you get to this black line, vertical black line. This is the point where the 0 orbital becomes meta-stable. Now it is not depleted yet. Why? Because in order to have depletion, you have to do many body tunneling, and the tunnel splitting here is exponentially small in the number of particles, so this will not happen. So actually you still have metastability, and the depletion happens only after you cross the 3 additional lines that are indicated here, and I will in a moment tell you what are these 3 lines. After you have the depletion, what you do is to reverse the sweep of the rotation and to go back to 0 rotation, and then you ask whether you come back to the initial condensation. Okay. So now I will summarize the bottom line, so to say. And after I summarize the bottom line, I will show you the results of the simulations that support the statements that I will now make. So I already pointed out that there is some value of rotation velocity for which we get metastability, which means that the condensate, well, the condensate is sitting in phase space, and initially it is sitting in a local minimum. Now, metastability means that this local minimum is not the true minimum. Because you cannot have tunneling because it takes too much time, then you have metastability in this local minimum. And then comes the Landau threshold. What Landau tells us that as long as you have local minimum, it is stable. But once you don't have this local minimum, once it becomes a saddle, well, then maybe you can get depletion. Why I say maybe? Because there is another relevant threshold in the analysis, which is dynamical stability. If you look on the Bogoliubov frequencies, then if you have a local minimum, then all the Bogoliubov frequencies are real and positive. If you have a saddle, then one of the frequencies is negative. But then at a later stage, at the dynamical threshold, they become complex, meaning that now the condensate is sitting in phase space in an unstable, dynamically unstable fixed point. So now you ask what will happen. Okay, let's for a moment assume that everything is described by the Hamiltonian of Bogoliubov. Then you ask what happens to the fixed point once it becomes unstable. For this, you plot Poincare section of phase space. And this is what you see here is a Poincare section of phase space at the energy of the cloud. And this Poincare section is when after you cross the dynamical border. So now the central point is unstable. Okay, I should say what are the coordinates here? Well, the radial coordinate in this Poincare section is the depletion coordinate, which means that the central point is no depletion, it is the initial state, and depletion means that the cloud goes out away from the center. So once you cross the dynamical threshold and it becomes unstable, and you see that there is a bifurcation and there is an island, and this island can shuttle the cloud outside. And so we call this mechanism of depletion adiabatic shuttling. And this adiabatic shuttling is reversible, because if we now decrease the rotation frequency of the ring, then this island comes back to the origin. But, and this shuttling, this is this threshold. It is called phi swap because this shuttling has to do with swap of separatrices. Okay. So, but now we have to remember that beyond Bogoliubov, we have additional terms that create chaos. So there is another mechanism to do the depletion, and the other mechanism to do the depletion is to spread through the chaotic region. This process is very much like free expansion, so it is very irreversible. This spreading through the chaos, which we call chaos-assisted depletion, this chaos-assisted depletion is a very slow process. So if you do the sweep not very, very slowly, you will not notice the chaos. But if you do the sweep very slowly, if you take the quasi-static limit, then this chaos will dominate, this mechanism will dominate, and this mechanism is very not reversible. And that's the reason why the quasi-static limit in the semi-classical analysis is not reversible. And now you ask, what happens quantum mechanically? Because up to now it was semi-classics. And as I will show you in a moment, in quantum mechanics, things are not so horrible. And the reason is that in quantum mechanics, the condensate can leak through the dynamical barriers before it is possible to do so classically. So because of that, the quantum depletion happens in a sense before, in a lower energy compared with the semi-classical simulation, and therefore the strong chaos that prevails at higher energies is not much experienced, and therefore the irreversibility is not so horrible. So now I will show you the simulations. So in the upper row, you see simulations with slow sweep of the rotation velocity. The vertical axis is energy, the horizontal axis is time. Up to the middle, the rotation velocity is increased, and from the middle, the rotation velocity is decreased back to zero. So if you have complete reversibility, if it is completely reversible, you start at the lower level at zero rotation, so you have condensation at zero momentum orbital, and then at the end you would like to have back the cloud at the lowest level. Well, this simulation shows that actually it is rather reversible, though there is a fraction of particles that stay at higher energies. On the right, you see the same simulation, but in a semi-classical approximation. So on the right, it is not quantum simulation, but classical simulation, so to say. And you see that there is very good correspondence between the two. So there is a fraction of particles that stays upstairs, but largely you can say that there is reversibility here. Now we do the same simulation, but much more slower. So now you see that it is horrible. Why it is horrible in the classical simulation? You see that here you have splitting of the cloud, and the big fraction of the cloud escapes before there is a shuttle to take it away from the origin. And this part, which is not waiting for the shuttle, so to say, is the part that is doing chaos-assisted depletion. So if you do it very slowly, instead of waiting for the shuttle, even before the shuttle, you start to do chaos-assisted depletion. And this is very irreversible, and the outcome is that you have spreading over many energies. But now you go to the quantum simulation, and you see the things are not so bad. And the reason is quite clear if you look on the timing of the depletion. You see that the depletion happens roughly when the energy is zero, unlike the semi-classical simulation where it happens at a later stage at higher energy. So the quantum depletion happens through leakage via dynamical barriers at a stage where you don't have too much chaos, and that's the reason why you have relatively good reversibility. Okay, these are nice pictures. Now we want to have something more quantitative. So let's plot the spreading in energy at the end of the protocol, how it depends on the rate of the sweep. So end state simply counts how many levels are occupied by the cloud at the end of the protocol. And let's first look on the black line. The black line is the semi-classical result. You see that in the semi-classical simulations, if the rate of the process is less than 10 to the minus 4, it is horrible, because then your particles are scattered over all the available energy levels. But if you do quantum mechanically the same simulation, there is here the blue line, and you see the things are much better. You will have some spreading over 10, 20 levels. This line is actually averaging over something that is doing wide fluctuations that we call universal quantum fluctuations. So The spreading is actually sensitively depends on the rate, on weighting, on parameters of the protocols. So due to interference, you have very strong fluctuations. But on the average, it is much better than the classical. Okay, I will skip over a more detailed explanation of what is going on. And I would like to just present briefly this caricature before I summarize. So, first of all, I would like to say the following. In order to have the adiabatic shuttling of Bogolyubov, you need a pairing interaction. So you have to keep in your calculation at least, let's say that we are talking about a general ring, you have to keep at least 3 orbitals. You cannot keep just 2 orbitals. You cannot keep, say, just orbital number 0 and orbital number 1 that cross each other. It is not enough. You will not have the Bogolyubov mechanism that we call the adiabatic shuttling. And for sure, you will not also have the chaotic mechanism that we call chaos-assisted depletion, because also chaos-assisted depletion requires 3 orbitals. 3 orbitals is 2 degrees of freedom. You need at least 2 degrees of freedom to have chaos. So the 2 mechanisms, 2 competing mechanisms that I have described, the adiabatic shuttling and the chaos-assisted depletion, requires a 3 orbital approximation. So there was some kind of naive thinking that if you have a rotating ring, you can do a 2 orbital approximation and then to analyze the process of the depletion using the paradigm of nonlinear Landau-Zinner transition. So no, it will not work. It is not the nonlinear Landau-Zinner transition that is doing the game. And you have to go to at least 3 orbitals in your approximation. So this is a general message. Okay, so now I can summarize. So a quasi-static protocol is in general not adiabatic and therefore not reversible, because in general, in system of interest, you have mixed regions of chaos and regular motion. So slowness, in a sense, is bad for adiabaticity because then you are exposed to chaos. In particular, I demonstrated a competition between adiabatic shuttling that is reversible and chaos-assisted depletion, a slower process that is very not reversible. So it follows that there is an optimal sweep rate, slow enough to have quasi-static behavior, but not too slow, because you don't want to be exposed to chaos-assisted depletion. And what we were looking for was fingerprints of this in the quantum dynamics. We realized that actually quantum dynamics, in a sense, bypass to some extent the irreversibility due to chaos-assisted depletion, because there is leakage through dynamical barrier that happens before we get to the strongly chaotic regime. And of course, since we have interference, we have universal quantum fluctuations, the spreading, the irreversibility is very sensitive to the exact timing of the protocol. I emphasize that in 2 orbital approximation is no, it will not give you the physics. I pointed out that the Bogolyubov approximation doesn't have chaos in it, and therefore it will provide you only the adiabatic shuttling mechanism. If you want also to see in your analysis the chaos-assisted depletion, you have to take also the non-Bogolyubov terms that generate chaos. And finally, semi-classical approximation, it gives very good inspiration, But when you go to quantum mechanics, it is not enough because there is a major breakdown of quantum to classical correspondence. So this is our recent work about this type of Bose-Hubbard models. These are other configurations that we have studied in the past, and here I give credit to other collaborations and students that worked on various configurations. And thank you very much.
Thank you, Doron. Was a very nice talk. And we have time for one question. I did not interrupt because you were coming towards the end. So, is any question? You have to open the microphone and speak up because I cannot visualize everybody.
I have one question, Vanderlei.
Okay, Ofer.
Doron, I think I asked you this before, but I will ask again. When you have a finite system, if you do quantum mechanics, you propagate forward in time and backward in time, and you should be back at the same wave function. This is still okay?
Yes, that's the question, whether you come back to the initial state, yeah.
And your answer is not?
Perfect reversibility you will not have, but you can quantify the irreversibility, and our quantification was simply by counting how many energy levels are in the superposition.
So you mean that for your time-dependent Hamiltonian, which is a rotating term, you will never come back to the same wave function?
It's not possible. I mean, you will have some spreading. Yes.
Okay.
Actually, even with 10 particles, it is very difficult, even on a computer, to simulate a quantum adiabatic process. Maybe with 5 you will manage, but it's very difficult. The condition is very difficult.
It's real irreversibility, more or less, always, right?
So yeah, you will always have some irreversibility.
Yeah.
And I hope that I answered.
Yes, okay, thank you.
Hey, thank you very much. Since we are trying to keep the time going to avoid problems with the plenary, I'm going to call now the second talk. And the second talk will be given by Wang. He's present here. Wang, where are you?
Okay, I'm here. Thank you.
Okay. And Wang is from the Shanghai University in China. And he's going to tell us about Wannier solitons in spin orbiter couplet Bose-Einstein condensate in optical lattice with a flat band. So, Wang, go ahead, and I will give a warning if I see that you are not towards the end when it's missing 5 minutes.
Okay, thank you. Hello, my name is Chen Hui. I'm from the Shanghai University. And now I'm a joint PhD student in University of Lisbon. And today I'd like to share our recent work, Wannier solitons in spin orbit coupling, BEC, in optical lattice with a flat band. Professor Yongping and Professor Kontov supervised this work, and PI already accepted this work. Thank you. Okay, here is the outline. I will introduce something about the band theory, gap solitons, and something about the Wannier soliton, and something about Wannier breathers. First, we need to know some basic idea about the band and the gap solitons. Let's consider 1D Hamiltonian here, with only include kinetic term and optical lattice here. And we know that in the absence of the lattice, the system possesses a translation symmetry, and the momentum k is a good quantum number. and the eigenstate would be the plane wave. And also, if in the present of the lattice, the system is no longer translation invariant, but it still maintains a discrete translation symmetry. And we know that the quantum momentum k is still the quantum number, and the eigenstate would be the Bloch state. And so on, we can find we can obtain the single particle dispersion. And here m is the binding index, and the energy would form the band with the band radius here and the band gap. Next, if we have the many-body interaction, the interplay between the spectral periodic and nonlinear dimensional evolution provides a lot of interest in physics. Particularly understanding-wise, the existence of unique soliton solutions that reside in the linear energy gaps here between the Bloch bands and so-called gap solitons. Such soliton-bearing systems are described by one auxiliary coupled CP equation with the periodic potentials. The attractive interaction enables solitons carried by the chemical potential mu loaded in the infinity band here, and or maybe in the band gap of the spectrum. Otherwise, if the interaction is repulsive, the solitons may exist only belong to the finite gap. And in a common situation, families of gap solitons replicate from one of the edge of a linear band, maybe the Bloch state. In the small amplitude limit, such gap solitons are governed by an NLS equation, which in fact dispersion is determined by the second derivative here, second derivative of the chemical potential with respect to K. Okay, this here is the gap soliton. Next. However, there are some interesting classes of the particular classes of lattice where one of the band is complete flight, or you can say independent of the quantum momentum K, which will lead to a localized eigenstate. And here I list some review papers about the flight band, if we are interested, and I show some examples. In figure 5, you can say it's 2D dice lattice, and the Bloch band here you can say is wave flight. And also in figure 6, it's 2D carbon lattice structure. You can see the band is also a constant. And in figure 7, you can see the diamond ladder, and the spectrum is also a flight band. And so it's therefore an open question if and how solitons may bifurcate from such flat band linear modes. And also, we want to know what's this linear models. Let's go back to the 2D carbon lattice. Here, with repulsive interaction, they find that families of localized discrete solitons bifurcate from the localized linear modes of the flat band with zero power threshold. Here we can see the straight blue line here from 0. This is amazing in 2D. And however, flat bands in continuous periodic systems were studied mainly in the tight binding limit, allowing for the approximation such systems by the discrete lattice. And we can ask question: what will happen if we consider continuous periodic systems, or we can say 4GP equation? So first, we need to find such a flat band. We have to know that the existence of perfect perfectly flat band in continuous system is impossible. Only nearly flat band can be found, so that concept of flatness itself must be specified. There's from previously work, we found that the extent of nearly flat band is characteristic feature of the continuous spin orbit coupling BEC with chosen parameters. To help you understand why. Okay, here is the Hamiltonian. This one is the spin orbit coupling strength. Here is the Rabi frequency. And here's lattice. To help you understand why, we can find a flat band here. Let's consider the case where omega is very big, greater than 1 and equal to 2 gamma squared. And neglecting the lattice, we can obtain the linear dispersion relation here. You can see that the band is nearly flat because the leading term here, k to the 4th power, can be quite small if omega is quite big, right? So that we use parameters delta, which is maximum minus minimum of the band, to calculate the flatness. And we see that if delta is smaller than 10 power minus 4, is a nearly flat band. This is obtained from the numerical simulation studies, and this is not a strict rules. And here we plot a finger the maximum of flatness of flat band we find in the gamma and omega plane. It's almost these lines, you can say. Okay, so now we have the flat band. Numerically, the gap solenoids of flat band can be found by means of Newton reduction as well as the difference method. And I'll plot here. Here is the density, here is the real and the imaginary part. In panel A, we can see the one peak here, one peak soliton, or we say that is a fundamental gap soliton, is confined to a unit cell. Provided the band is flat because the solution is quite close to the band. Meanwhile, the system also supports families high-order solitons here, different. Also, you can see we also compare the gap solitons with the linear winding function, the dots here. We can see that they are quite similar, right? We can see that they are almost the same. We guess that the gap soliton with the flat band should bifurcate from the winding function. So we plot this finger. Its projection of fundamental soliton on the winding function. You can see the most one. So on, we call this flat band solitons, linear solitons. And next, we want to construct a theory about this linear solitons. And here is the definition of the linear function. And if we apply the Hamiltonian to the linear function, we obtain that these equations. This coefficient here is determined by the flatness of the band, and the linear function is not exactly the eigenstate of our Hamiltonian. And to describe the soliton families fabricating from the flat band, we look for a solution of the equation in the form of mixed expansion. That is the linear function for the lowest band and the block function for other bands. Here, you say the main part is the linear function. And we're substituting this expression into the GP equation and projection on the linear function. We find obtain these coupled equations here. And we should notice that we use the condition, this Fn here, should be very small because we are focused on the flat band. So we only leave this part. This part is a relationship between the chemical potential and the particle number n. And also you need to say this chi, the coefficient chi is depend on the interaction. We will use this condition next. Okay, so finally we have the result, theoretic results here, and we plotted here, see the circle lines for all results. We also compare them with the numerical results, that lines here. We can see that they fit very well. And at the same time, we also investigate the symmetry and the stability. And we have two main results here. First, the full symmetry solitons A and B. We use the solid line here, A and B. They are stable. And the solitons with the broken symmetry, they are unstable. The first result. And the second, we see that linear soliton families replicate at the n equals 0 and mu equals mu 0 from the linear functions. And this is our flat band linear models. And the next, enhance the stability of the linear solitons as their existence in the constant limits suggests a way of construction the oscillation solutions. And we're substituting this three model on SAS back into the GP equation, and in terms conjugate the variables, and which are the phase difference, the phi, and the fraction of the total number of atoms, the n, and we obtain the dynamic equation here, and the corresponding Hamiltonian. Usually this Hamiltonian is very similar to the three-level models governing atoms in the three-well traps. But here we see that the coupling here is related to the interaction. So the coupling in our system, in our case, is nonlinear. And first, we simply can consider the dynamic of the two Ham brazers here. You can see here is something a function of G. So you can see that one interaction here, the interaction go to 0. The period will go to infinity, that the brazier will vanish. And next, here we give the implicit expressions for the station points here. This one is for the use of the oscillations here. And this one is the transition points. These 2 points. And here is for the cycle trapping. Maybe here. And we also show this blue circle here. You can see this evolution. And the cycle trapping red one is here. And also we also plotted a figure about the difference and the period here. You can see the two defined region. One is the distribution oscillation, and one is our self-trapping. And furthermore, the direct numerical simulations show that not all feathers of dynamic in the vicinity of the separate trace can be captured by this two model. You can see here is a little different. So we plot this figure we can see the derivative of the purist here. It only appear with attractive or repulsive. Only one. For the physical where point of where the sensitive of the system was in the worst vicinity of the several objects can be explained by the directions of the localizations and thus the effect directions and of the W linear solitons upon the effect of either attractive or repulsive interaction. And in summary, we find that the linear solitons have shapes described by the linear functions, and the weights remain practically unchanged for both attractive or repulsive. When solitons share the whole symmetries of Hamiltonian, they were found to be stable. And this allows for the construction of linear blazars, which usually represent the non-linearly carved condensate colors. Fair models will capture the evolution of linear blazars. So maybe in the future we will focus on the 2D or stirrup. Okay, thank you.
Hey, thank you very much, Wang, for the nice presentation. And the paper is now open for questions or comments.
Mm-hmm.
You have to open the microphone and start to talk if you want to ask a question. Well, so it was very clear, Wang, so nobody has questions about. So thank you very much. We're going to move it on. We still have a few minutes left. So I don't know if Haish is here. I think so. Let me scan the people. Oh, I don't see Haish or Bar or Furman from Texas University. Well, maybe we should then wait a few minutes because maybe it is in another seminar, right? And we should wait the time.
Linda, you have to make the microphone active. Your microphone.
My microphone? No.
Of Linda.
Linda Haish is here then.
She's here, but
okay.
she's speaking, but her microphone is mute. Maybe you can unlock it.
I cannot unlock, but she can unlock.
No.
Yeah, you can. You did.
Okay. Yes. I tried to.
So Linda Haish from the physics department, University of Texas in Austin, and thank you very much for coming. And she's going to tell us about intrinsic thermalization of a honeycomb optical lattice. So, Linda, you have the 30 minutes, and if it's necessary, I will give you a warning. Otherwise, I'm going to let you go. You can start anytime you want.
Thank you very much. So let me just try to adjust my own screen here a bit. Okay. So I'm going to talk about intrinsic thermalization of the honeycomb optical lattice, and this was work done with students, Aaron Barr, Ace Furman, and then an ex-student, Max Porter, and it just got published in PRE. So there's only one system that's been mathematically proven to be chaotic and ergodic, many-body system, and that is the hard sphere gas. And the proof is based on the proof by Sinai for the Sinai billiard, where you have a hard disk and you look at scattering of particles off a hard disk, periodic boundary conditions. And the scattering is chaotic, ergodic, everything. And so this translates into the hard sphere gas being an ergodic system, a chaotic system. That means that all states of the gas with the same energy are equally probable. In the 1990s, Srednicki, based on quantum mechanical derivation, rigorous, showed that a dilute hard sphere gas has a single particle distribution function, which is Maxwell-Boltzmann for the semi-classical limit, or it's Bose-Einstein or Fermi-Dirac for degenerate Bose or Fermi particles. But and so therefore note that the so-called ideal gas equation of state that we all have seen in physics from the first courses is really an equation that only applies to a hard sphere gas rigorously as of now. And it's not really an ideal gas. It's particles colliding very drastically. So the world around us is not a hard sphere gas, but it's almost totally thermalized. And so the big question that many people are looking at is, how does the thermalization occur in systems which are not hard sphere gas? So that's what I want to talk about. And I want to focus on the particular example of ultra cold cesium atoms confined to a honeycomb optical lattice. And I'm going to use parameters from old experiments by the Raisin group on cold cesium atoms in optical lattices. But they looked at one space dimension. I'm going to look at higher space dimension. So cesium atom has a D2 line, and the lasers are tuned so they're near resonance with this particular line of cesium. So you can imagine the cesium atoms as being two-level atoms in this counter-propagating standing waves of light. And so very quickly, the Hamiltonian you can write in terms of energy of the excited states of the atoms, then the translational energy, then the energy of interaction of the particles with the field, which causes transitions between the excited and ground state of the two-level system. So if you put in pairs of counter-propagating lasers targeted at angles with one another, you can construct an electric field which gives you the structure of a honeycomb lattice. And if you go to the rotating frame of the laser light, so a frame oscillating with the frequency of the laser, you come up with this Hamiltonian in that frame of reference. And then with that Hamiltonian, you can find the spatial dependence of the cesium atoms in that lattice. And so if you write the Schrodinger equations for the ground state and the excited state of the cesium atoms, they're coupled. But if the detuning of the laser is far enough from the atomic resonance of that two-level system, then you can eliminate these space derivatives and time derivatives and write the excited state in terms of the ground state, and you come up with a Hamiltonian for, just the ground state motion of the atom. So they interact with the laser beam and transmit momentum, but they don't, for the most part, get excited. So this is the Hamiltonian of a single cesium atom in this lattice. And the potential energy that the atoms see for the case we're considering looks like this. There's a term that's cosine x. There's a term that depends on z minus x over square root of 2, and another cosine that depends on z plus x over the square root of 3. Now, we can go to dimensionless coordinates or dimensionless units, and I'm using all the numbers for cesium in this optical lattice, the same parameters used in those old experiments by Mark Raisin. And then in dimensionless units, we're going to take the amplitude of these cosine terms in the interaction to be 20. And here is the optical lattice, and it's a beautiful, perfect honeycomb lattice. The dark regions of the phase space, these dark triangles, are for negative energies, which range minus 20 to 0. The saddle points are at 0 energy. And then these pillars, these are positive energy pillars, which are like Sinai pillars. they have surfaces of negative curvature, and they will cause chaos. And they go from 0 to 160. They get soft up at higher energies. So the strong effect of the C9 scattering starts to diminish as you go to higher energies. Okay, so that is the system we are looking at. Now, I'm going to first look at the classical dynamics, and we're going to focus on the behavior of the cesium atoms in the dark triangle. I can't really see my own slides here because I have all these pictures on the side. But anyway, so the unit cell for the classical case is this triangle surrounded, formed by these dotted lines, which run from the peaks of 3 neighboring C9 pillars. And in the middle is this dark triangle, and whose energy ranges from -20 at the minimum up to 0 at saddle points here, which are these points on the tip. Let me just say that this triangle, equilateral triangle, by itself, if it was a billiard, would be integrable. And the C9 pillars by themselves are chaotic. So it's a very interesting mix of dynamics in this system. But of course, everything gets soft as you go to the edges. Now, let's look at the classical dynamics for energies -20 up to 0. That's the dynamics in this dark triangle. The way you analyze that classical dynamics is to do a canonical transformation from, and that's what we're going to do here, from Cartesian variables px and x to action angle variables. So I'm going to, if you notice, px squared plus 2u cosine 4x over square root of 3, that is the Hamiltonian of a pendulum. And what we're going to do is sort of diagonalize that pendulum, the x pendulum, and then rewrite the Hamiltonian. Now, the canonical transformation from x and px to the action variable jx and theta, angle variable theta, is given in terms of Jacobi SN functions, which themselves depend on complete elliptic integrals of the first kind. And they both have a modulus, which depends on the energy of this x-dependent pendulum and the amplitudes in the total Hamiltonian, the U naughts. Now, why do I do this? Well, if I rewrite the Hamiltonian in terms of these new canonical variables, then it's written in terms of the Jacobi SN function. And the Jacobi SN function is a periodic function which can be expanded in an infinite Fourier series. And the coefficients in the Fourier series fall off fairly fast with this parameter L. And so it's fairly large, of order 1 for L equal 0, but it's a fraction, a very smaller fraction for L equal 1, etc. So it falls off fairly fast. So in terms of this Fourier expansion, I have written the Hamiltonian for a single cesium atom in this optical lattice in terms of an infinite number of these pendulums now. And why do I do this? Well, these pendulums provide the mechanism for the transition to chaos if it will occur. So let me do a side note here. I want to come back to the so-called paradigm Hamiltonian. This is a Hamiltonian where you have two pendulum structures. You have one a px squared plus minus cosine x, and another px squared minus cosine x minus theta. So there are two pendulums in this paradigm Hamiltonian. And you can locate, so a pendulum has a structure. It has a libration region where the pendulum just oscillates back and forth, and then a rotation region where the pendulum oscillates around in a circle, and those two regions are separated by a separatrix. And the width of the half width of the separatrix is 2 times the square root of the amplitude of the cosine, the U1. So in principle, in a simple world, these two pendulum separatrices would touch when the sum of their half widths is equal to 1, because they're separated by a distance 1 in the momentum space. But if you actually look at a strobe plot of the dynamics of this two resonance system, you see that it's very complex. In fact, these two primary resonances interact to create a whole self-similar nonlinear structure of pendulums to the smallest scale in the phase space. And as you move as you increase the amplitude of these cosines, you start to see the effect of these higher order resonances overlapping, and when they overlap, they create chaos. And so this is the origin of the onset of chaos in these systems. And here you see for the spacing of 0.72, you start to see very small scale chaos, and spacing, I can't see this part of my slide. So at about, I think it was 0.97 or 98, you see that there's a huge chaotic sea, and you see the remnants of those two primary resonances embedded. So that's why we want to expand the Hamiltonian for the dynamics below the saddle points in terms of these sine waves, because then we can look at where chaos might set in. And what we find is that actually only for energies less than zero, only two resonances, primary resonances, affect the phase space. The L equals 0 appears through the whole energy interval below the saddles, and then the L equal 1 resonance pops in as you get closer to the saddle coming up from below. And so if we look at the surfaces of section, they follow what we expect, that there's no chaos for lower energies because there's no overlapping primary resonances to generate those higher order fractal structures. So energies minus 15, for example, you see the phase space. You can see the effect of that one resonance here in the structure of the surface of section. I'm plotting px versus x every time a trajectory goes through z equals 0. And even at energy minus 10, you see the phase space is very regular. You do see the effect of the single resonance, but on the scale I'm looking at here, no chaos. We get up to minus 5. Now we start to see the more complicated structure of the system, and chaos sets in. You still see the remnants of those, the original resonances from lower energy. Now, if I go to higher energy, E greater than 0, then the CNI columns start to take over. And for energy E equals 0, we see chaos. We do still see remnants of resonances, but we see a large scale chaos. If we go up to E equal 20, now it's total chaos, pure chaos. And even up to energy 80, pure chaos for this whole energy interval. We get up to 120. Now we're getting up towards the top of those CNI columns where they start to soften. And now we start to see structure coming back in the phase space. Now, this is what happens to a single cesium atom in this optical lattice. Okay, now what about the quantum mechanics? Well, for the quantum dynamics, the unit cell is twice as big, and it's based on the unit cell of graphene. So we follow pretty much the analysis you would have in graphene. So the unit cell now is sort of this squashed rectangle. It contains two of the classical triangle unit cells. And same Hamiltonian we had before. The unit cell area is square root of 3/2. We can introduce the primitive vectors, which are vectors along these dotted lines in space, and then the reciprocal lattice vectors. This is the same analysis you would have for graphene. The unit cell itself has an infinite number of eigenstates. That is, this lattice has an infinite number of energies whose spatial structure repeats every unit cell of this infinite lattice. And that's given by this expansion here in terms of the reciprocal lattice vectors. But then we know that there are eigenstates whose structure is greater than a single unit cell, but which will repeat over a number of unit cells, and those are Bloch states. And so we can find all of the energy eigenstates of this lattice. The best way to get at it is through the Bloch analysis of the Bloch states, and which involve the Bloch momentum, which gives you an indication of the distance through the lattice over which it is required for the energy eigenstate to repeat its structure. And then there are some particular values of this block momentum K, which are always basically the only ones you see in the literature. There's the K point, which has a block momentum 2/3 B1, reciprocal lattice vector B1, and 1/3 B2. And there's the M point, which has this 1/2 B1 plus 1/2 B2. These are involve symmetry lines of the lattice. And what I'm going to show you now is the energy levels for a range of values of block momentum going along the line from K from K point to the gamma point. The gamma point is the unit cell. So all states on the gamma point repeat every unit cell of this lattice. So we're going to go from along the line of block momentum from K to gamma, then gamma to M, then M to K, and show the energies for this continual line of wave vectors. And that is the band structure of this lattice. So here are the energy bands for energies below the saddle points, energies -20 to 0, where the system was largely integrable. And there are only 6 quantum states below the saddle points. Remember, I'm using real parameters for cesium in an optical lattice whose frequencies resonate with that particular line of the cesium atom. So I'm using real experimental numbers here. So there are 6 energy levels below, and the lowest pair has a band structure going from K to gamma, M to K, which looks exactly like the band structure of graphene, the lowest 2 energy states of the graphene lattice, or nanotubes, if you like. What's interesting is that the band at the K point has a Dirac point for this system. And at a Dirac point, really interesting point, a lot of people looking at it, the dispersion relation energy versus the block momentum is linear. That means for energies and wave vectors around the Dirac point, the cesium atoms behave like photons. They have essentially no mass, and so they have a very interesting dynamics. Then the other 4 states occur up at higher energy, around -5, and there are 2 flat bands. I don't know if those are interesting to the previous speaker. He was talking about flat bands, but there are 2 flat bands, and then 2 more bands which look like the lower energy graphene, and another Dirac point higher up. Now, if I go to look at the bands for energy 0 to 12, then this is what they look like. And so I'm going here from the top right corner, energies around 0.75, and the top left corner, the bottom right corner is energies up to just around a little above 11. You see these Dirac points appearing. There's for each one of these pictures, there's a Dirac point. Very strange behavior of the cesium atom. 1 cesium atom in this lattice. I want to emphasize that. And okay, but if I go to higher energy, where the Sinai pillars start to really take effect of the dynamics, and we saw that complete total chaos. Here's what you see. And now these are a little misleading. The top 2 plots and the bottom left corner plot are for smaller energy intervals than the bottom right plot. But what you see in these plots are a lot of avoided crossings of the bands. And here you see really drastically on this bottom corner where I have a bigger energy range, pure chaos classically, and you see all these avoided crossings. These avoided crossings are a signature that the underlying system is chaotic, and the quantum system is behaving as if its Hamiltonian were a random matrix, the signature of quantum chaos. Now, what happens when you have these avoided crossings? So I'm going to switch now to an older work we did on a square array of C9 columns. And the unit cell is just the square around a single column. And I just want to show what happens at avoided crossings. This on the left is, and by the way, this was work by Max Porter, Alex Barr, his sister, Aaron Barr, his sister, and me several years ago. So here's the band structure going from the gamma point to the K point. And so along this left vertical line is the gamma point. These are the energy eigenvalues for the unit cell states. But what you see, and I'm going to just focus on a little energy region here from 60 to 80 and pick out 3 of those states from the band, and here they are. And so this is the gamma point here, eigenstates inside the unit cell, and I have one at energy above 70, I'll call it B, below 70, C, and still below that, H. And these are the plots of the energy eigenstates in the unit cell, which is now square. And this is fairly high energy, so they start to have some structure. But notice here, as we increase K heading towards the K point, there's an avoided crossing between the 2 lowest states. And if you look at what happens to those states beyond avoided crossing, you see that there's been a switch in the behavior and a mixing and muddling of the eigenstates. And so basically this state that at the gamma point circles around the C9 column now has switched up to the higher block state, and etc. And again, there's another avoided crossing between the upper 2 levels here. If you move further on, and you see again, when that happens, there's again a kind of switching, mixing of the states. So what happens at these avoided crossings is the block states get all mixed up. And the energies, the single particle cesium atom states are quantum chaotic. But those are single particle states. There's no thermalization. You need to have thermalization of the n particle system. That's thermalization. So what happens? Well, there's a hint to this from some work of other authors, Ehrman, Vergini, Shepelyansky. This is one example that this has been looked at a little bit. They took particles in a C9 oscillator. And a C9 oscillator is one of these hard circular columns or disk embedded in a harmonic trap. And harmonic trap has different coupling in the 2 space dimensions. So a single particle state in that C9 oscillator is chaotic. It has energy spectrum which is similar to that of a random matrix. That's a definition of quantum chaotic, random matrix, universal behavior. But they found that they put on a very weak coupling, a Gross-Pidievsky interaction, absolute value psi squared times psi, and this strength parameter beta. And they found that for very small values of beta, well, there's no thermalization of the n particle system. They put n particles in this oscillator, no thermalization. But as they increase beta, the strength of this fairly weak nonlinear coupling between the particles, they suddenly had a transition to thermalization. The n particle system became thermalized, ergodic, to very good approximation. So the bottom line is our cesium atoms. So we found that a single cesium atom up in the region where the C9 columns are giving single particle chaos, that if those cesium atoms interact, and we know they do, at very low energy, it might be more Leonard-Jones type interaction, have enough energy to see their hard core, that interaction can cause that the cesium gas in this optical lattice to thermalize. And so this is likely an important mechanism for thermalization of the world around us. If the single particles are in some potential, which makes single particle chaotic, then interaction between those particles, even if it's weak, can cause thermalization of the n-body system. So it looks like we don't need hard sphere gas to make up the world. We just need structures that have asymmetries that give chaotic single particle behavior and then interactions. Okay, so thank you very much. And by the way, thank you for the organizers to recreate this conference. I'm very happy to see that it started up again. Okay, so that's it.
Thank you, Linda. It was shorter than I could not even need a warning for you, so we have time for questions.
I talked really fast because I was worried I wouldn't get through it in time.
But you did very well. I think it was very clear. We have any question with the participants? Well, I don't see anybody raising their hands.
Yeah, I have a small question.
Oh, okay, Alice, please.
This fact that when you have single particle chaos and then in a many body system, even weakly interacting, the system will thermalize?
May thermalize. So you have to look at it.
Is it a theorem, or which is the status of this result?
I think the status is there are several examples now where that's been seen. That points the direction to understanding how these systems, which are not don't have hard sphere interactions, could thermalize. There's not been a lot of work on it, but there are several examples that show that this may be the mechanism for it.
Okay, thank you.
Yes, I have a question.
Go ahead.
Yes, is this thermalization somehow dependent on the dimensionality of the system? Namely, is it easiest to do it in 3 dimensions with respect to 1 dimension, for instance?
Well, in 1 dimension, you don't have any chaos. So you need two degrees of freedom to even start.
Yes.
And if you have 3 or more degrees of freedom, chaos becomes much simpler.
Yeah, I was thinking about, say, 1 dimension. Well, okay, yes. Okay. Spatial dimension for a nonlinear Schrödinger equation, I'm thinking, where you have a lot of degrees of freedom, actually.
Yeah, you will need some kind of non-linearity to cause the single particle state.
No, because I'm thinking something like the Fermi-Pasta-Ulam problem, where in 1D somehow you have some freezing and no thermalization, while in 2D or in 3D it's much easiest to get it.
Yes.
Okay.
It's easier to get chaos in higher dimension.
Yes.
It's hard to avoid it, actually. Single particle chaos.
Okay, thanks.
Yes.
Now, the mechanisms of thermalization depends very much on the symmetry where you are, right? That's why you get into this.
Yeah. Yes.
Okay, so if there is no further question, I think we should move. I think Sunayana is here, right?
Hello. Yeah.
Okay, fine. So Sunayana is from the LPHYS' Research Center for Theoretical Physics and Astrophysics in Israel. And thank you very much for coming and presenting your work to us. And she's going to speak about condensates breaking up under rotation. So, Sunayana, please go ahead.
Yeah, thank you. So my today's talk is on condensates breaking up under rotation. So outline of my today's work presentation are, I'm going to give a brief introduction about rotating condensates, and then I'm going to give a brief summary of the method that I have used to simulate various ground state properties of bosons, which are weakly interacting, that is the multi-configurational time-dependent Hartree approach for bosons. And then I'm going to benchmark MCT-DHB in a rotating frame to show how accurate the method can be. And finally, my results I'm going to discuss my results in like two parts mainly. So the first one is like breaking up of the condensate into two clouds and twofold fragmentation in a barrierless anharmonic trap. And further, we will study the breaking up to several clouds and explore higher order fragmentation with trapping potential with more complex form. So finally, I'm going to conclude my result in conclusion slide. So successful experimental realization of rotating BEC has paved the way to explore various quantum features that expands from emergence of quantized vortices, vortex nucleation, emergence of quantum fluctuations, fractional quantum Hall effect, and many more. But those domains are mainly in mean field domain. And along with this, recently there have been studies of breaking up of fast rotating objects that extends from astronomical domain, for example, galaxies and supermassive rotating stars, to the quantum systems in nuclear physics. In atomic physics, the emergence of superfluid flow of a rotating quantum gas has also been experimentally reported. So, however, there exist a very few studies of rotating BEC in many body domain. So in our work, we explore the many body as well as the mean field properties and how rotation affects it. So to simulate various ground state properties, we are considering barrierless anharmonic traps with discrete rotational symmetry in 2D, namely an elongated trap, which is basically a barrierless trap with an elongation in the x direction and threefold symmetric trap, and finally a fourfold symmetric trap. So my work has been published in this reference. So MCT-DHB approach. So this is a variational approach and very accurate, where the key idea is to use the time adaptive basis state, where the coefficients and the orbitals are basically time dependent. So in our work, we have considered 10 bosons that interacts very weakly via Gaussian interaction of the form this, with interaction strength of the order of 0.1. So in our work, the dimension we are working in a dimensionless atomic units. So these are the main references for MCT-DHB approach. So to study various properties such as energy, density, and like quantum correlations, we basically use one body density matrix of n boson state given as this. And with the diagonalization, we can get the eigenvalue equation like this, where the normalized eigenvalues are we termed it as natural occupation that characterizes the degree of condensation and fragmentation, and shorted in magnitude as N1 is the first natural occupation, which has which is greater than N2, and so on. So we are using MCT-DHX software, which is an open source version of MCT-DHB algorithm. These are the references of MCT-DHX software. So benchmarking of MCT-DHB in a rotating frame. So basically, we consider an exactly solvable many-body method, and where we benchmark and see the accuracy of our results. So the many-body Hamiltonian in the rotating frame breathes says this. Here, first term is the one-body potential, and this is a two-body interaction term. So if we consider a harmonic interaction model, where basically the trapping potential and the two-body interaction term are harmonic in nature. So in a rotating frame, the energy is given as this, energy without rotation minus some modification. And however, position variance and momentum variance boils down to that of a non-rotating system. And here the angular momentum variance is also affected by rotation, and this is given as this. So here we benchmark the energy, ground state energy per particle with few rotation frequency. Here omega is the rotation frequency, and also a very sensitive quantity that we all know, many particle variances of position and momentum operators and angular momentum operators. Here you can see, so without with the inclusion rotation, if we increase the rotation, we see the numerical and analytical value are exactly matching till 6 digits. So similarly, for position variance, we can see that with inclusion of rotation doesn't affect the convergence of the system. And finally, this is the position variance in x and y direction. And this is a angular momentum variance, which is more sensitive to any perturbation, which is also exactly converged. So now our main study is now we are going to show you how with rotation there is the breaking up of density and also fragmentation of the system occurs, though the bosons are trapped in a barrierless trap, which is an which is an elongated trap that elongates in the x direction, and the trapping potential is given by this. Here we have used 4 orbitals, and the rotation frequency ranges from 0 to 2. So this figure shows with the inclusion of rotation for small rotation frequency, this density remains as a single core, and there is no any other features. With further increase in the rotation frequency, that we can term it as a fast rotation around 1.2, it is observed that the density clouds breaks up into 2 clouds. The density core basically breaks up into 2 clouds. With further increase of rotation, that's for around 2, the density breaks up more, and the clouds are separated more. So this is the many body density. So we also observe that the mean field density shows the similar pattern. So now the question is whether it will lead to a fragmentation or not. That's the concern. So we will see in the next slide. This is the natural occupations. So we have used 4 natural orbitals, but we have shown only 2 leading natural orbitals, because the other 2 natural orbitals are non-occupied, basically. So here we have seen with the inclusion of rotation till certain value, the system remains condensed. With further increase in rotation, here we see some features, and then again moves back to condensed state. And then for faster rotations, the system transits from condensation to purely two-fold fragmentation, with N1 and N2 around 50%. So this features is we termed it as a resonant behavior feature. So we all in the insert it shows the zooming behavior of this natural occupations. Here we can observe that in the transition in the resonant regime, there is a transition from coherence to loss of coherence, and again buildup of coherence. So whether this resonance regime is a mean field effect or is a purely many body effect or mean field effect, that we will know in the next slide. So let's discuss about the angular momentum behavior. So here with inclusion of rotation till certain rotation frequency, the angular momentum remains very small. With further increase in rotation, that is around 1.2. So it's the rotation frequency that belongs to the breakup of the density cloud. Accumulation of angular momentum in the system occurs, and which keeps on increasing with further increase in rotation. Here we saw a feature what we call as a resonance regime. So here we have plotted the zooming plot of the resonance regime. Here the blue line depicts the mean field angular momentum, and the red is the many-body angular momentum. So we can conclude that the resonance condition, resonance feature is not purely many-body. It occurs also in mean field angular momentum. However, the mean field resonance has a narrower width and like narrower peak. However, in many-body, it has a wider width, and mean field occurs a bit fast faster than the many-body. So now let's discuss about the, like, we know that variance is a very sensitive probe of a correlation that characterizes the quantum fluctuations present in the system. So let's see how variance is affected by rotation. So this is the position variance along x and y direction, and here the momentum variance along along x and y direction. So the x position variance, in the x position variance, we can observe that like mean field variance and many-body variance coincide till around 0.9, which depicts there is no correlation in the present in the system. However, further increase of rotation frequency, mean field monotonously increases. That depicts the spreading of the density that we have observed in the density plot. However, in the many-body, we see some features, and then it increases very slowly, and finally it decreases for faster rotation. That depicts that signifies the emergence of fragmentation in the system. So basically, so here also we observe that this resonance feature is present both in mean field and many-body position variance. However, they have an opposite direction, and this however, a y position variance is almost similar in case of mean field and many-body, which signifies there is no it doesn't y position variance doesn't involve in any excitation, so it's basically frozen. So now let's discuss about the anisotropy that present in the position variance. So to describe the anisotropy present in the position variance can be computed by two facts, like comparing the variances along x and y direction, and also by comparing the variances at the mean field and many-body level, that characterizes whether the anisotropy are alike or opposite. That's all. So it's observed that for slow rotation, x position variance is smaller than the y position variance at the mean many-body level, and at the mean field level, x position variance is also smaller than the y position variance, which shows the anisotropy at slower rotation is alike. However, for fast rotation, we observe an opposite anisotropy. That's like x position variance is smaller than the y position variance when computed at the many-body level. However, the x position variance at the mean field level is greater than the y position variance at the mean field. So basically, mean field and many-body position variances are not similar. So it signifies presence of opposite anisotropy in the position variance for faster rotation in an elongated trap. So further we study the momentum variance. Here we can see the momentum variance at the mean field and many-body level are similar in the x direction. So apart from these resonance features developed in the resonance regime, however, the position variance or momentum variance in the y direction shows it remains similar at the mean field and many-body level for smaller rotation. However, at after 1.2, mean field increases monotonously and many-body decreases for faster rotation. So basically, we can conclude that rotation induces excitation position variance along the long direction and momentum variance along the narrow direction. So let's see whether anisotropy is present in the momentum variance are alike or opposite. So we can see that for slower rotation, it has alike anisotropy. As you can see, many body and mean field variances are similar. However, for faster rotation, similar to the position variance, momentum variance shows opposite anisotropy. So rotation induces opposite anisotropy both in angular momentum, both in position and momentum variances in elongated trap. And this is a new feature in our study, which is not present in a simple double well that with very simple double well. So another feature that we can conclude from this plot, like this is the plot from many body first natural orbital, and this is the mean field natural orbital, where we can see like the orbitals changes its symmetry with the onset of resonance in the system, and that is prominent both in many body orbital and along with the mean field orbital. So now we consider more complex systems, which has higher order discrete rotational symmetries, and see whether the system, whether this density clouds breaks up into more, whether the single density breaks up into more several clouds, or whether higher order fragmentation is possible, and how the correlations behave with rotation in this complex system. So here we have considered a threefold symmetric trap of the form this, and we have considered three orbitals, and here the frequency and the rotation frequency ranges from 0 to 2.5. So as you can see, with the inclusion of rotation for smaller rotation, the density has a single core. With further increase of rotation, the density slightly split into three vertices of a triangle. For faster rotations, the density core breaks up into three clouds. So we want to see further, like whether this breaking of density, threefold breaking of density, is related to fragmentation of related to onset of fragmentation in the system. So here we plotted the natural occupation as a function of rotation frequency. Like as we can see here, the blue line depicts the first natural occupation, and red and green depict the third and the second natural occupations. So you can observe that as we increase the rotation, the first natural occupation goes around 60%, and the second and the third is around 20%. So basically, there is a transition from condensation to threefold fragmentation. However, this threefold is not purely threefold fragmented. It's like partially threefold fragmented. We have observed that with further increase of rotation for the stronger interaction, you can achieve a purely threefold fragmented state. Unlike elongated trap, where we achieve a purely twofold fragmentation for a very small rotation, around 2. We further study the variances. Here you can see that here the mean field variance increases with increase in density for increase in rotation frequency for high rotational frequency, and the many body variance first increases and then gradually decreases. However, one more important feature is like here the X and Y mean variances are similar, are coincide with each other, which describes the rotational symmetry of the system is preserved. though we include a very strong rotation. So similarly, in momentum variance, we can see like mean field variance increases with increase in rotation frequency, and many body variance decreases after first increases and then decreases and then slightly again increases. So we further consider a more complex system which has a threefold discrete symmetry and check whether we achieve more breakups of the density or like higher fragmentation is achievable in that system with the inclusion of rotation. So this is a fourfold symmetric trap, which is considered as this. Here we have considered 4 orbitals, and the rotation frequency ranges from 0 to 2. Here, as you can see, as earlier, for smaller rotation, we observe a single density, and with further inclusion of the rotation, further increase of the rotation frequency, the density clouds, the density core breaks up into 4 clouds. So here is the question is like whether this 4 density clouds lead to a fourfold fragmentation of the system. So this is the natural occupations with rotation frequency. We have plotted all the 4 natural occupations. The blue one is the first natural occupation, red and green are the second and the third natural occupation, and black one represents the 4th natural occupation. So we can observe that with the inclusion of rotation for very faster rotation, there is a transition from condensation to a partially fourfold fragmentation in this fourfold symmetric trap. So, however, this is not purely fourfold fragmentation. So we also observed that the variances, both the position and momentum variances, show similar pattern as we observe in the threefold symmetric trap. That is like where we can say that the rotational symmetric is preserved for the system. So conclusion of my today's talk is like rotation can be used to manipulate various degrees of fragmentation. Also, in elongated trap, it is observed that the ground state density breaks up into 2 clouds with rotation. The splitting of density is followed by the acquisition of angular moment fragment. Is also like followed by emergence of fragmentation and also the acquisition of angular momentum. And it is also observed that the ground state exhibits opposite anisotropy both for many particle position and momentum variances when computed at the many body and mean field levels. The rotation squeezes the position variance along the long direction and momentum variance along the narrow direction, thereby producing a unique many body effect. Again, for threefold and fourfold symmetric traps, we observe that the ground state density eventually splits into 3 and 4 clouds. That follows by emergence of threefold and fourfold fragmentation. Side by side, the rotation leads to a transition from condensed to threefold and fourfold fragmented condensates, respectively, at the many body level of theory. So I want to acknowledge my collaborators, Axel and Ophir. Thank you.
Thank you, Sunayana.
Yeah.
Nice presentation, and we have time for a few questions.
Yeah.
Well, I have a question.
Yeah.
What about the formation of quantized vortices induced by the rotation? So why you don't see? It seems to me that you have not observed the formation of quantized vortices. Why?
Yeah, because we have seen the vortices. Like we didn't explore it much, but we are planning to explore it for this is like the ground state study. We want to explore it in the dynamics part.
Okay. Okay, thank you.
Well, I have a comment. It's more, I see that Axel is your collaborator.
Yeah.
Some time ago, we did a turbulence experiment in a BEC, holding a harmonic trap. And if you keep it pumping energy, after establishing the turbulence, what we see is a breaking down in many islands of condensates, which I think is somehow related to this kind of multimode approach, right?
Okay.
And my question then is how those lobes talk each other. I mean, the atoms are tunneling all around and they are distributed among those lobes.
This is like ground state study, so we don't know how the system will behave for like dynamics. So this is for our future study, actually.
Yeah, because they claim that in high TC superconductor, things that perturb the system are breaks in domains of superconductivity and is equivalent for superfluidity. And I always associate that with this granulation of the superfluid, which we're going to go back to explore more now this situation. All right. Is any more question? No? Okay, then I want to thank you all the speakers of this part of the section. I just want to remind you that we are coming back at 4 p.m. UTC time. You make the calculation for your local time. And then we're going to have 3 nice talks in this section. So please, I hope you all return at 4 p.m. UTC time for continuation of our workshop. Thank you very much. And we have a break now. And then there is some plenary talks. You can join whatever you want on those talks. Thank you very much. See you in a few hours. Bye-bye.